Welcome back, and today I'm going to be looking at this DSP device, which is by Analog Devices. I've looked at a number of ways to implement digital control. We're going to look at digital filters today, and some, well, I wouldn't say simple, but some basic ideas in digital filtering, and look at the actual implementation rather than just a Matlab simulation. So this is the chip is on here actually, which interfaces to your computer, and then it's got an I2C interface to this board here. And I'll just look at the board on here. I'm just going to get the information. Here it is here. The Analog Devices Evaluation Board, eval ADAU 1787Z, and it's got this nice board which gives us stereo inputs and stereo outputs. There's two processors, not on that board but on the small board here. There's a fast processor and a other processor which I'm going to be using. I can't get the fast processor to run at the moment. I think it might be something to do with software problems. I don't think it's hardware. I did manage to get both channels running at one time. At the moment I've only got one channel running, but it's good enough to show how digital filters work. So what I'm going to do is I'm going to show you the software, and then I'm going to do some theory and Matlab and so on, and come back and actually illustrate how a digital filter working. So this is the software I'm using. A few things first. It needs a hardware configuration, and so you select this tab, and it's already got this there, and I think it has. You connect the particular chip into the USB here. That's just selecting the I2C. That's the address of the I2C that it's using, I believe. And that's the chip ADAU 1788, which is down here. And if you've got different ones for different processors, you can select them as well. You notice it's done in the signal flow form. If you look at a schematic I've got here, which is a program in other words, it bears more than a passing resemblance to LabVIEW, doesn't it? I mean, here's the flow from input to output. This is the ADC. We've got two of them on each one of the processors. And I'm only putting one out, so it's only one input. I haven't selected this one. I could if I wanted. We'd come up with an error because it's not connected. I'll just show you if I do that. Oh, it's still doing it even though I don't connect it. Okay, connect it. That's all right then. So channel 0 is going through a volume control, and then it's going through an FIR filter, which we'll talk about in a minute. But this one's 314th order. That's only zeros, of course, no poles to speak of. And then the output is channel 0 on the board. I'm using this processor here, the 1780S, not the fast one. It's just because I can only get that to work at the moment for some reason. Down the left-hand side is blocks that we can use, just like in sort of LabVIEW. So, there's adaptive mixers, basic DSP, for example. There's a multiply. I can drag it across here, but notice it doesn't appear as a multiplier. I've got to click and then do add algorithm, and that's my processor IC1 Sigma, and there it is. It appears. I won't be able to connect that to my multiplier either, because it's already connected to there. So it's not like LabVIEW in that sense. We've got to have what's called a T connector, which is there somewhere. If I can find it, I think it's under System and T connector, and delete that, and then we connect from here to the T connector, and then from there to there, and then I think it takes two outputs, isn't it? So We can connect that to. Sometimes it's a bit difficult and tricky to connect. Yeah, there we go. So that's connecting one source to two outputs. You can't just, it won't just like LabVIEW connect on the line and put a dot. You need this T connector to do whatever you want to do. So you can build up some kind of program using this. This is my filter and that's my output. And so I could multiply by some other signal or do whatever I want. I could create amplitude modulation, for example, or double sideband suppressed carrier, albeit at a low frequency. Over here on the left-hand side, basic DSP, there's a delay. I'm going to use that in a minute. It doesn't, like LabVIEW, put an icon with Z to the -1 on it or whatever. It just shows you that here, some delay of one sample. You can have two samples or whatever you want. And there's the input and there's the output. So I can have delays. So once you've got delays and multipliers and gains as well, again, that gain doesn't show up. So I've got to select it. It goes green when you select it. And then add algorithm, sigma, gain, no slew. And then I've got my gain now, you see. Then you can make up filters. Or in programming, there's a signal add if you want to add do addition. So we've got multiplication, addition, and so on. We've got ready-made filters, which are already here, which is things like shelving filters, it looks like. The emphasis. A lot of this is made up for audio applications, people buying it for special effects and so on. It's got an adaptive filter here, which is normalized LMS, it's called. It's got two inputs and two outputs. That's quite powerful, obviously. So far, I can't see how to do basic programming like vectors and so on. There's my I/O, so in ADC inputs and outputs. That's for my current process, my Sigma DSP. These are level indicators, numeric displays. It's quite useful. So it'll show me in real time the level of the signal. There are also graphs. There's mixers here. Again, because it's audio, there's a lot of stuff on mixers, demultipliers. It's got sources, so you can create, say, a square wave and then shove it straight out the D to A here. Or you could scale it first. Very much like LabVIEW, there's a triangular wave. You can do a VCO, voltage controlled oscillator. Oh, it's not appearing again, so I selected add algorithm sigma. There it is there. So I could make a phase lock loop maybe here as well, I'm thinking. But let's delete that for the moment. And I'm going to have a look at a little bit of the theory of digital filters. So here on my book, which is Rudiments of Signal Processing and Systems, and I'm assuming you know something about Z transforms. If you've been doing a course on DSP, you would have come across something like this. This is a second order finite impulse response, meaning it's got a finite impulse response. It hasn't got poles. When you've got poles that are not at the origin, at least on the Z plane, then it becomes an infinite impulse response, or IIR filter, infinite impulse response. This is a finite impulse response filter. It's only second order. It's got three coefficients, the second one of which is 0, so it's 1, 0, 1, because the coefficient of Z to the -1 doesn't exist. And here we then have our transfer function, h of z is 1 plus z to the -2. We can multiply by z to the -2 on the numerator and denominator and get z squared plus 1 over z squared, in which case we've got complex zeros at the square root of plus or minus the square root of plus or minus 1. Sorry, I beg your pardon. Plus or minus the square root of minus 1, or plus or minus j, or I if you're a mathematician. And poles at the origin 2, which don't do anything. So all FIR filters have got poles at the origin, but we kind of don't need them to know that information. We can see what it's doing by taking the frequency response. Theoretically, it's 1 plus e to the minus 2j theta, because z to the minus 1 is e to the minus j theta. And we just get this 2e to the minus j theta cos theta. And I'm going to be demonstrating this with the processor in a minute. So we take its magnitude and its phase. Its magnitude is 2, magnitude cos theta. So it's got this kind of notch thing. That's a quarter sampling. That one is half sampling plotted on Matlab. That's quarter sampling. So at quarter sampling, so in my case, if I'm sampling at 48 kilohertz at 12 kilohertz, the output should go down to some zero magnitude and then start going up again. And notice that phase is linear phase. Not true of all FIR filters, but this particular one is, because it's got symmetric coefficients. Actually, I just realized that should, oh no, that is correct. The sign is negative there. It's got symmetric coefficients 1, 0, 1. It's symmetric about, there's the impulse response, symmetric about the center point. If it was 1, 0, minus 1, it would still be symmetric, but it would be, it would be an odd symmetric rather than even. This is even symmetric. But we can calculate this one by hand very easily. Now, because it's got this straight line phase characteristic, it makes these kind of filters are very useful for filtering digital type signals where you want to preserve the edges of the signal. I mean, it doesn't do it perfect, but if you don't have linear phase, it doesn't necessarily preserve the signals as they're going through the filter. Basically, what it does, it acts like a time delay. So it does the filtering and it delays the signal at the same time. It's actually more like a group delay than a time delay. A group of frequencies, it's got this delay. So I'm going to show you this working now. Remember, the coefficients are 1, 0, and 1 here of the impulse response. So I'm going to enter that. So now I'm going to look at a much more sophisticated version of FIR filter design. The one that's probably the favorable one in the profession, which is the Parks-McClellan design, which happened in the early 70s, late 60s. Oh, sorry, that's here, Parks-McClellan. Now, this uses the work of a French mathematician, the name of Remez, who wrote a paper in 1934 about a special minimax algorithm. It's not normal least squares in that it doesn't just minimize the error, it minimizes the maximum value of the error, which is a bit like sort of Chebyshev, I believe, kind of approach. It's quite complicated, but we don't really need to. So it's called the Remez exchange algorithm. That was the original optimization paper, and Parks and McClellan used it to design FIR filters. And there's a bit of a theory to this, of course, but it turns out that we don't actually need to know all of this to actually make use of it. Here, because we've got a Matlab script here, this one will actually design it. You just need the sampling frequency and a few other parameters. I'm going to design one using Matlab. I'm just going to boot up Matlab, and first of all I've got to find my program, which is here, and boot up Matlab. And it's actually quite a simple program. Most of it's just putting in the data. So here's the program. Sorry, I can't get it any bigger at the moment. But it's got a sampling frequency of 48 kilohertz. And I'm going to put it's going to be a low pass filter, which has got a cutoff of 10 kilohertz. And it's got a stop band frequency of 10,500. And it's got passband ripple of 0.01 and stop band ripple of 0.01. Passband amplitude is going to be unity. And it will work out the order. I don't know what the order is. And once I've got the order, it gives me the coefficients of the filter B, and then I'm going to write them to a text file. I'm just going to run this program, which is PM. It tells me it's 313th order. That sounds a lot, and it is actually, but not for today's DSP devices. So here, that's as in dB, so that's unity, and then it shoots down, and it goes down 60 dBs. That's 1,000-fold in amplitude. So you'll barely see anything on the oscilloscope when we do this, but just to give you an idea of what it is. So we'll go ahead and, oh, sorry, I should point out, here's the actual coefficients themselves appear in a, oh, where's it gone? I'll just try and find there it is. These are the coefficients, 300 and something of them. And at first sight, you might think, oh my God, I'm going to have to type them all in. But because they're on a file, we can actually load them into the Sigma Studio, which is quite nice. Right, so let's go and do that. Right, back to the hardware. And I've got an oscillator here, or a function generator. It can produce sine, square, triangle waveforms. And next to it, I've got my oscilloscope. I'm just going to feed my sine wave straight into the device. Well, this is the device here, the input, and the output is there. Just ordinary 3.5mm connectors, and nothing more than that. So first of all, let's design our filter. We already did that. I hope you can see this. It's maybe a bit difficult to see. Try and zoom in on it because I'm not on the screen capture at the moment. So here's my input here, channel 0. I'm just putting a volume control in there, just anyway, gain and control anyway. Here's my filter, and then here's my output. So I'm just going to add some, just click table and put 101. Remember, that was the coefficients of the filter we had, which was the cosine characteristic, the 1 plus z minus 2. Now it's done. And then I'm just going to connect. Oh, yeah, I always have trouble connecting these things. Always seems to want to. Oh, there we go. To the output, and we're done. And then I just press this button up here, which downloads it, links it, compiles it, and so on. And that's it. Now I go to the scope. I'm not going to go down. Remember, the sampling frequency is 48 kilohertz. I can set it to other frequencies, but you know, for example, 24, 32, and 96, and up to 768, believe it or not. It's a very powerful processor. But here I've got, I'm going to, you see it's saturating at the moment. So I'm going to turn down the volume control here. I don't know if you can see it. That's me in real time. It's just quite nice to do. So it's not saturating, and then if I, oh, of course it's, the trouble is it's triggering, so I'm going to have to get rid of the trigger. There's a trigger gone away, so it's not triggering, so I can see You see it going down as I go up in frequency here. See if I can zoom out a bit to show you. As I go up in frequency, it goes down, then it goes back up again. Down, and it goes down about there to 0. If you have a look on here, that's 12 kilohertz, and lo and behold, that's quarter sampling. A quarter of 12, 4 times 12 is 48 kilohertz. So it's doing what it's supposed to do. That's low frequencies, then it's going up to quarter sampling, down to 0, and then back up again. Now I'm going to do the more complicated filter, which is a minor change here. So I'm going to go to the table and click on that, and I'm going to load table values. I think that's, oh, there it goes. Then I've got my file, and it's all done, but it's not done it actually. I've got to do update, I think. Oh, it's still not done it. Oh, save. I've already saved them. Sorry, I'm just going to, I'm having a bit of trouble there loading it, so I'm just going to come out and come back in, because I've already done that to save you the trouble of seeing me fiddling around with it. So Sigma Studio 4.7. There is a technique to doing that, but I'm not going to. Okay, so this is one I've prepared earlier, as we used to say on children's TV programs, and it's got 314 terms in there. There's the table. So I'm just going to run it again up here. Again, the sampling frequency is 48 kilohertz. Now let's just remind ourselves though what the frequency response should look like. It should be 0 dB, so it should be unity gain until 10 kilohertz on this. That's the scaling on this. And then it goes down with incredible slope down to minus 60 dB, so it's 1,000-fold attenuation. Oh, that's the wrong one there. I'm running it now, so it should be running. And so I'm at 4 kilohertz, 5 kilohertz, 7, 8, 9. Oh, there, look at that. See how sharp that is. That's 10, beyond 10 kilohertz. You can't see anything. I'm sure we could expand the scope and see something, but you won't see much. You can see nothing but noise. Now, one other interesting thing, let's put a square wave in at a low frequency. Same, just select square wave here. Now look at that. I'll trigger it again. Isn't that interesting? That's the classic Fourier series and so-called Gibbs phenomena. You don't get that with a, let's say, an RC network. If you put a pulse through an RC network, it would be curved here and then flat. If it was second order, it could have ringing, but you don't get the symmetry here. The reason for that is the very sharp attenuation and the linear phase. The phase is not disturbing the shape of the waveform. Of course, as you go up too far, it eventually becomes a sine wave, which makes sense because you've filtered out all the higher harmonics. As you go down in frequency to very low frequencies, you can see that's interesting happening. It's just like our Fourier series analysis. Okay, so that takes us to the end of this demonstration on the real-time demonstration of digital filters. I hope you enjoyed it. See you next time. Thanks.